This presentation is about the series of Jupiter mutual events coming up essentially between September this year and August next year. Next slide. Mutual event, an eclipse or occultation of one satellite by another satellite. They only occur when the plane of the orbit is edge onto the Earth, and that occurs for Jupiter. It occurs for about a 12-month period every 6 years. Saturn, you get about a 12-month period every 14 years. Uranus, it's a rather longer period. Measuring and analysing the light curves leads to very precise measurements of the relative position of the satellites, and they can be used to improve knowledge of the orbits and long-term orbital variations. One of the things about having an Earth-based telescope observing these things is you've got a long time base. It's a limitation of satellite stuff is the satellites tend to be only there for a limited period of time. Next slide. Some example occultations. These are output from the graphics out of Occult. Top one, Ganymede occults Europa on January 14th. You see Ganymede there's rather larger than Europa, and it's completely occults it. And the bottom one, which the text has got displaced, but it's Io occults Ganymede on January the 1st. So Io is little one, and there it's just a small partial occultation. Next slide. Eclipses. Top one is Europa eclipsing Ganymede. With the eclipse, the inner clear circle is the umbral shadow. The grey annulus is the penumbral shadow. And the size of the umbra and penumbra depends upon the distance between the two satellites. And that depends upon whether they're on the same side of Jupiter or on opposite sides of Jupiter. Now, the first one is Europa eclipses Ganymede. And I venture to say that both of those are on the far side of Jupiter when that happened, because the penumbral region is fairly small. The second line, that's actually Ganymede eclipses Europa. And you can see there that the umbral region is very small and the penumbral region is large. That tells me that Ganymede and Europa are on different sides of Jupiter. And the bottom one is Callisto eclipsing Io, and with that eclipse there is no umbral region, it's purely a penumbral shadow. Next slide. This is a summary of results from previous seasons. You can see there that's 6-year intervals from 1985 to 2009. We've increased the number of sites involved from the 28 in 1985, which would have been almost all professionals, 74 last time around, large number of amateurs, and 457 light curves. The 2009 season, last season, there were 370 observable events, of which 172 were observed. That's almost 50%. They observed 74 sites with 457 light curves. Next slide. That's a simple graphic of where people were located. Because this program comes out of Paris Observatory, there's a high concentration of observers in Europe, with a reasonable number in North America, but they're spread around the world. Next slide. You get involved in this program and the results will get published. This is written by the professionals at Paris Observatory, but all the observers get listed as joint authors. On this slide, the North American observers I've got measured in, indicated in red boxes. The Australasian observers are in green boxes. I've probably missed a few in there. As you can see, there's quite a few observers. And that's quite a reputable magazine, journal, that's Astronomy and Astrophysics. Next page. Now, hopefully this works. Okay, this doesn't work. If you download this PowerPoint, the black bit on the left is an animated GIF file showing a mutual event in real imaging. A few doors down from me, like it's literally 5 minutes walk, the guy by the name of Anthony Wesley, who's made a name for himself with the detailed imaging of Jupiter in particular. He discovered the impact of something onto Jupiter several years ago, which made headlines around the world, and then he also recorded something else flashing into it. His telescope is Steve, if you can get it to run, Steve, without too much, it's an interesting thing to show. So, see if you can show it. The telescope he's got there, for the likes of people that believe in flocking and so forth for installation of the telescopes. Anthony has his telescope tube made of aluminium for high conduction. He has thermoelectric cooling to keep the temperature of the glass within 0.1 degree of atmospheric temperature or something. Direct imaging of a mutual event, taken with a 16-inch telescope on the right. Okay, let's move on. If you have the PowerPoint, you can also download or look at a YouTube which actually shows a mutual occultation event, but time is moving on, so I think we'll skip that, and you can look at it on YouTube or whatever. Observing requirements for these events: driven telescope, because these events last a little bit. It doesn't need to be an equatorial mounting. So you can use an altazimuth mounted scope, just as long as it's driven. Time to 0.1 of a second, the standard occultation stuff. Video with timestamp of some sort, even if it's just the start and end, but it's you need a time base, a reliable time base. Recorder, VCR, computer, any of the usual things, and a frame grabber to convert to an AVI file. Just stock standard occultation stuff, except you've got to plan on observing for rather longer than an asteroidal occultation. Next event, next slide. Measuring tools, line movie or Tangra. Line movie from memory was originally developed for mutual events. Tangra with what the recent developments by Risto with Tangra are important developments, particularly modelling the background, because with bright Jupiter there, the effects of Jupiter as the distance of the satellites from Jupiter change during the course of events, and the way the background subtraction works with aperture and point squared photometry. They're important things that need to be dealt with. Then there's, well, last time around I had a thing called line movie average to do binning and to reduce file sizes. I need to find out a bit more about what the latest version of Tangra does in this area. But we have tools to facilitate all of that. Next slide. The observations reported to the IMCCE, which is effectively Paris Observatory. It's a simple text report, and you attach the CSV file that you get out of your measurements and optionally a plot so they can see what's going on, and then they will duly analyse it. Next slide. We don't collect the reports. All the reports need to go directly to IMCCE. Observing issues. You need to observe for about 3 times the predicted duration of the event, which is typically about 4 or 5 minutes. So you're looking at about 10 to 15 minutes of observation. If you don't have compression running, you've got a huge ABI file. One of the concerns that the Paris Observatory people expressed is with video cameras, they have some concerns about linearity of a video camera response. Need to make sure that the gamma is set to 1, but when playing around with gamma, you've got to look at the whole recording system and not just one element of it, because gamma tends to be set and unset at different points. And then image motion of the moon in your field of view. You need to be careful that try to have good tracking and have the image in a stable position in the field, because if you have any big netting across the field, that will cause light variations, which, if you've got any significant image movement, and if that can affect one moon more than the other, and that can give rise to false changes in light variation. So good tracking is important. Next slide. For observing, IMCCE recommend the use of a red filter to reduce the sky background. So that's something to take on note. A thought I've had, and if you've got a methane filter, maybe it might be worth trying a methane filter. They're not cheap, and they'll give rise to very long exposures, but that's something we could experiment with. An issue that IMCCE are keen on is having several independent observations of the same event, so that you've got more than one light curve to compare and say, well, these 2 light curves we've got 2 light curves and they're fully consistent with the shape, so the shape is real and not instrumental. If you've just got one light curve, then there leaves open some issues about, is the cause of the variation in the a real light variation in the Jovian system, or is it instrumental in nature? Independent recordings of the same event gives you independent light curves which can be compared. Best to avoid saturated images of satellites, but if it's just a little bit of saturation, when you do the maths about what's involved with saturation, a little bit of saturation of the central couple of pixels is not a great problem, but try to avoid large saturation, and or use PSF measurement, which is what Tangra does with the new functionality. Next slide. Closest to Jupiter can create problems with the sky background correction. Remember the way aperture photometry works is you have a central aperture which measures the star or the moon plus the background around it, and then you have a larger annulus around it which measures the background. The usual assumption which is made with that background subtraction is that the background light is uniform across that background aperture. When you've got a bright light source such as Jupiter nearby, that assumption is an invalid assumption, and it means that the light variation across the background aperture is nonlinear, and it has a high order term, and that means that your background subtraction starts having effects which are dependent upon changes of the distance of the object from Jupiter, and can give rise to anomalous changes in the measured brightness of the object. It's this stuff which has driven Risto to modify Tangra and put a fair bit of work into this to model the background light from when doing this stuff, so that you can model the background light intensity across the background aperture, so you can do a proper background subtraction. So for that reason, Tangra would seem to be the tool to use to make the observations, to make the measurements of this forthcoming set of events. This background subtraction issue is a really important advance. Next slide. Yeah, I picked up some example light curves of, these are real light curves showing the good and the bad. And they're light curves which IMCCE has published in some of their literature about observing these events. The left-hand one is a good one. It's observed in 1997. The right-hand one is of the same event, but a different observer, different setup. The left one is a pretty crappy. The left one's a pretty good event. The right-hand one, pretty crappy, really, in terms of what you can get out of it. Next slide. The next slide actually quantifies what you can get out of these. Left-hand one here, a good light curve. Right-hand one, very noisy, bad. Left-hand one, it's the time of minimum plus or minus 7 seconds. The right-hand one, uncertainty is 53 seconds. Magnitude drop, left-hand one, uncertainty 0.018 of a magnitude, right-hand one, 0.2 of a magnitude. We're aiming to generate light curves like the left one and not like the right-hand one. Next slide. Sometimes the light curves are non-symmetrical, and these are two examples from I have there. The left-hand one, you can see the left-hand side. Well, there's a clear difference between the left half and the right half, and that's due to the phase defect on the relevant satellite. That's Jupiter 3 occulting Jupiter 2. The right-hand one, the blip at the bottom, is due to surface effects on the satellite being occulted, which was Jupiter 4. Next slide. An interesting thing, and it hadn't really gelled in my mind, but this illustrates it well. The beginning and end of an eclipse is smoother than for an occultation. Eclipses, because of the penumbral shadow, tend to have a very gradual onset and finish, whereas occultations tend to be much sharper at the start and end. On the other hand, occultations, the maximum depth of an occultation is 0.5 or 0.7 of a magnitude, I forget which it is, whereas an eclipse, the magnitude drop can be a large number, 4 or 6 magnitudes in rare circumstances. Next slide. This is probably an issue more if you're doing it with a CCD, standard CCD camera, but it illustrates the problems of measuring these types of events next to a very bright object where you don't have suitable reference stars nearby. Here are 4 light curves of the same event. The vertical scale is the same in all of them. And look at the difference in the magnitude drop that has been reported by these 4 different things. This was back in 1997. So this wasn't done with video, but fundamental problems with the data reduction, data analysis. So on one hand, you've got the bottom left one, the magnitude drop is almost 6 magnitudes, whereas the one to the right of that, the magnitude drop is about 0.2 of a magnitude. It's a factor of about 100 to 1 different. Interesting. Next slide. With video and time insertion, we should not have this issue. But again, 2 light curves, same event. Trouble is the time difference is out by several minutes. Time scale across the bottom is exactly the same. Left-hand one is 20.56. Right-hand one is 20.51. That's 3 or 4 minutes difference in time. Bit of an oops situation. So time is really important, but hey, as video occultation stuff, we're familiar with that. Prediction accuracy. Occult currently uses a theory by J. Lieski. It's for Jupiter satellites. IMCCE has developed a new theory which they use for their predictions. I'm currently trying to implement their theory. It ought to be simple, but I'm not replicating the positions accurately enough yet. But this is a comparison of the central time of the events between the IMCCE predictions and the occult predictions. Most of the times are within about 10 or 20 seconds of each other for mid-time, and that's for events where you're looking at observing duration of 10 or 15 minutes. There's a few events with high time differences, like the order of 3 or 4 minutes, but you'll find those events that have durations that run into hours. They're very slow-moving events. So you can work on the basis that predictions, one way or another, will be accurate certainly within a minute, and more likely much better than that. Next slide. There's a dedicated web page at Paris Observatory. That's the address there. Next slide. What to expect in the US. This is a summary of what's visible in Eastern USA. Western USA will be sort of similar numbers. You've got Jupiter opposition on February the 6th, and it's fairly well north, so it's up in the sky a long period of time. So you've got a lot of events through January, February, March, because Jupiter's up all night. Couple of interesting events listed at the bottom there. Two events occur while the satellite transits Jupiter's disk. On December 23rd, you've got Europa occulting Io. So that's, you'll have, if you can see the disks of the planets, of the moons on the disk of Jupiter, and you can do, you'll see them merge in front of Jupiter. Whereas on January 25th, Callisto will eclipse Io while Io is in Jupiter's disk. So what you'll see there is actually Io catching up to the shadow of Callisto, and then going into the shadow and going faint as it goes into the shadow, and then coming out of the shadow. Anyone that's got access to really good imaging equipment that wants to try observing or recording those, would be interesting events to record. And last slide wraps it up. Next slide, last slide. That's it. Any questions? Yeah, Jan Manek has commented about informed me there's some 200 additional events which didn't get into the first batch and should be published. My understanding, I have every reason to believe that Occult has produced them all. I know there's somebody in Europe has done a comparison of the Occult results with the IMCCE results, and there's two different lists in Paris Observatory, and the comparison was done with the longer list, and they're all there. He picked up some issues with the Occult. He also identified some issues with a couple of the IMCCE events where, whilst the event is predicted, the satellite being a cold draw eclipse is actually not visible at the relevant time. It's just part of the problems of predicting these things. Chad asked, any planned updates to the iMovie average program? The short answer is yes, but I want to get on a handle on what Risto's done with Tangra. And Ted has asked, what is the iMovie average? One of the issues with measuring these events is trying to optimize the signal to noise, and you got a lot of scintillation noise. The iMovie average program I did read the CSV file that came out of iMovie and allowed you to bin the data and then to normalize the results using one of the other moons. So if you measured a reference moon, then you could use that as a normalization reference. And that improved the signal to noise no end, because we don't need to have measurements made at 25 or 30 frames a second. We need the measurements made at sort of 1 or 2 a second. So there's plenty of room for averaging or binning the data to improve the noise and get a better signal. As the normalizing was to deal with the issue of changes in atmospheric transparency during the course of the event, change in altitude, all of which changes the measured brightness, and trying to get measurements which are unaffected by peripheral things. Unfortunately, there's a range of issues still floating around there. I suspect there's an issue with color, the color response of the cameras. If you've got the camera, the event going down sort of relatively low altitudes, then you've got subtle color changes in the satellites as they go through thicker atmosphere, and then That's going to be factored into the photometric response of the CCD chip and how that affects the different satellites. So there's a range of reasons why, if you're not careful with how you process these, you can finish up with light variations which are caused by things other than the Jovian system. And we're not very good at getting rid of them all. Yan has asked if I recommend to report bin or normalised data or the original numbers. From memory, I always reported bin data, and I also sent IMCC both normalised and unnormalised data, so they could choose. But certainly binning, because otherwise you finish up with huge files with a whole heap of noise, and binning is an extremely valid way of reducing the noise. Thanks all. Much appreciated.